This is topic 49, inverse functions. So notice that f of x and g of x are inverse functions, and they have the following properties, which, as you can see in A, this is a composition function. And notice that both of these, you get x for both of these. I'm going to do example 1 here in a minute, so hopefully that'll make more sense. And the second property is that if you're looking at the table of f of x, for example, and you have AB as one of the points in this table, then if you look at the table of the inverse, those 2 points are in reverse. You would have B first and you have A. Okay, so let me just go straight to example 1. Now, if you have this function, y is equal to x cubed, and you're trying to find the inverse of that function, what you would do is switch the x and y, and then you would solve for y. Alright, now we're going to solve for y by taking the cube root of each side, or by raising each side to the 1/3 power, which is the same. Alright, so this one right here would be y is equal to x to the 1/3 power, or the cube root of x is the same thing. Alright, so remember that this right here is my inverse. So I'm going to write this with this notation. So the inverse of function f is equal to x to the 1/3 power. Okay, now after that, to make sure that they're truly inverses of one another, what I have to do is I have to grab function f, and inside of here I have to plug in the inverse function. So I'm going to plug in the inverse of function f. So all that means is that if I have function f, which is this one, remember, and if I plug in x to the 1/3, so now what I have is x to the 1/3 power raised to the 3rd power, and when I do that, I get x. Alright, now I'm going to do the opposite. Now I'm going to grab the inverse function, and inside that inverse function, I'm going to plug in f of x. Alright, so when I plug in x cubed into the inverse function, notice that I also get x. And if those two functions have this property right here, then that means they're inverses of one another. Alright, so and finally, to validate the point, what I can do, for example, I can pick any point, it doesn't matter. If I pick, for example, for f of x, if I pick a point, alright, so if I pick a point like 3, right? So if I pick a point 3 and I plug it back into this equation, right, 3 cubed is 27. Alright, so without me doing really any work, I know that if these are inverses of one another, if I plug in 27 into the inverse function, which is this one, right, so if I plug in a 27 to the 1/3, that gives me 3. So notice that they're the same, almost exactly the same, except for the x and y's here. The x and y coordinates are switched. Alright, so that's what this is saying. So this is just a refresher. It has almost nothing to do with calculus yet. Alright, so now we're going to try to find the derivative of g of f of x equal to x. Now remember that on this one, they're telling me at the beginning that g of x and f of x are inverses of one another. Alright, so just keep that in mind. So if I take the derivative of this, I would have to do a chain rule. Alright, so it would be the derivative of the outside function is g, defined at the inner function, which is f of x, times the derivative of the inside, which would be f prime of x. And the derivative of x would be 1. Okay, so that's what that is. Now, just doing a little bit of algebra here that you may not understand why I'm doing that, but is relevant to what we're going to do next. If I divide both sides by f prime of x, and I get the derivative of the inverse at a certain y value is equal to 1 over the derivative of the original function. Alright, so I'm actually going to write this out. So the derivative of the inverse is equal to 1 over the derivative of f. Alright, so this is actually a very important formula right here, which is actually what we're going to do next. Alright, so on this one, notice that they're asking me, remember this means a derivative, find the derivative with respect to x of the inverse of function f at a. Alright, so let's break this down. Function f is this one. Now, do we know the inverse? The answer is no. Could I solve for the inverse? The answer is yes. But what this is saying is that what we can do, alright, so if I take the derivative of the inverse function, that would be the same thing as 1 over the derivative of function f. Alright, so let me show you what I mean, alright? Let me just go ahead and, well, when am I going to take the derivative here? Okay. I'll come back to this in just a second. Alright. Okay. I'm going to take the derivative here. This is 3/4 x squared plus 1. Okay then. What else? Okay, so let me at least write that over here. Alright, so if that was all that you had to do, that would be easy, of course. But this is not that easy because I actually want to know the derivative of the inverse at this point f. A is some kind of constant number, right, that I'm not familiar with. So what I'm going to do here is notice that a is 3. So really what I'm trying to look for is a derivative at 3. And this is when it gets weird, so I'm going to leave this blank right here. This 3, you are not going to plug that in here because this a coordinate is not the same coordinate as this x. This is actually the y coordinate of this. So that's the weird part. Alright, so let me explain this here. So if the inverse has a coordinate AB, that means that I have some point, this 3 comma something else that I don't know. Alright, so I don't know what that is. That's what I'm trying to look for. But I can find that point easily because I know that on f of x, I have the same points, but this is b and a, right? So if I have this, that means that I would have some x value, which is equal to 3 for the y. So how do I figure out this value here? How do I figure out b? Well, the way to do that is telling me right here, right? If f of x, if the y value of f of x is 3, then what is x? So what I need to do is I need to grab this original equation, and I need to set that equal to 3, and then I need to solve for it. Okay? Now, you can use the calculator obviously for this, but if you use your calculator, right, you figure out, or you can just look at the table if you want, or look for the intersection on your calculator, wherever it may be. Right, you figure out that on the table, that x coordinate that gives you 3 is actually 2. Alright, so this right here, I'm going to highlight it, if I have a highlighter. This right here is what I need in here. Okay, so this right here would be a 2. That would be a 2. So again, I'm going to highlight that so then next time when you're looking around, you hopefully notice that something's different about that. Alright, so that's what I'm going to plug in. So I'm going to plug in a 2 here. And then all I have now is just a constant number. So all I have to do is to evaluate this at 2. Alright, so just be careful. The only trick to this is that if it's asking you for 1 point here, you have to go to f of x and do what I did here, which is set that equal to that number that is given to you, and then solve for x. Alright, so now I can solve this. So now I have the derivative of the inverse at 3 is equal to 1 over, this would be 1 over 4. Notice that will be 4. 3/4 times 4 is 3. 3 plus 1 is 4. So this is the answer. So hopefully that makes sense. I know that was kind of a mess, but it's one more time, okay? If you have whatever value is here, this is actually the y value of this. So what you need to do is you need to go back to this f of x function and set that equal to that a value that are given to you. And then you solve for x. And once you figure out at x, then you're going to plug that in into your derivative. So that x is going to be your derivative. Sorry, this is going to be the x value that you found here. Okay? And then once you do that, then it's problem over. Okay, now let's go to the back. I'm not really sure what the purpose of graphing this is, but one thing that you must definitely remember is that the inverse function of sine can be written as arcsine, or sine of y is equal to x. So you're actually going to see this more often than not, the arcsine of x. So remember, anytime you see arcsine of x, that's the same thing as the inverse of the sine function. Alright, so just to quickly graph this, they're asking us to graph this right here. So to graph this, what I'm going to do is I'm actually going to graph sine of x. That's what I'm doing here. I don't know why. Okay, so that's what that will look like. Again, remember the sine of 0 is 0, so that's how I know where to start. Anyway, so to graph this right here, which is the same thing as this, okay, what we're going to do here, actually let me write some of the points. Negative pi, so this is negative pi over here. That'd be negative pi over 2, 0, pi over 2, I don't know, negative 1, 0, 1, I'm not plugging another one here, 0. Anyways, so if you have this, what you're going to do is you're going to switch the x and y here. Okay, so if you switch the x and y, notice that I have, let's see, this would be pi here, this would be 2 pi, so at negative 1, so this is your x value now, at negative 1 you would have pi over 2. Oh my gosh. Hold on, let me start at 0, 0 and pi. This is confusing. Okay, so I'm starting here. 0, 0. Let's say negative pi. Okay, so yeah, negative pi over 2 would be here, so that would give me something like that. Okay. So if you did something like that, obviously this is not a function, so you would have to restrict the domain and the range. And you can restrict the domain and range to like negative 1, comma 1, which is what I had here anyway. But the range, I would have to restrict that to pi over 2, negative pi over 2 to pi over 2. I'm not really sure what that accomplishes on this one, but we're going to find the derivative of the inverse of y is equal to sine of x. Alright, so the first thing we're going to do, just like before, we're going to switch that. Okay, and by the way, this is going to lead me to one of these formulas, so just hang in there. Right, you're not going to have to remember this part necessarily. So if I take the derivative of that, this would be implicit differentiation. Remember, so that would be the derivative of x with respect to x is 1. The derivative of sine y with respect to x would be cosine of y times dy dx. Okay, so if I solve for dy dx, I would get that dy dx is equal to 1 over cosine of y. Alright, so this doesn't look like any of these, right? So what you would do if I want to get this in terms of x, one of the things that I can do is use this trig identity and again, all I'm trying to prove is that one of these is true, or that what I'm telling you is true. So if I subtract sine squared from both sides and I take the square root of each side, I get cosine of y is equal to the square root of 1 minus sine square y. What else do I have here? Okay. So notice that right here, I'm going to make a note that if sine of y is x, then sine square of y is equal to x squared. Okay, so the cosine of y is equal to 1 minus x squared. And that's how you get that to be in terms of x. Okay. So notice that this right here would be 1 over square root of 1 minus x squared. Alright, so that's sort of how I'm trying to prove to you that this is true. Alright, now having said that, I'm going to show you how to actually use these three formulas. Alright, so remember, these are the derivatives of the inverse of sine, the derivative of the inverse of cosine, and the derivative of the inverse of tangent. Alright, so what you're going to do here is that this u right here, when you take this right here, du dx, this is the derivative of the inside. Okay, so that's the derivative of the inside, while u is the inside. So let me show you how to do this, alright? So this is actually a lot simpler than what I did just earlier. So notice that right here I'm taking the derivative with respect to t of the inverse tangent function. Alright, so notice that locate your inverse tangent function is right here. This inside right here would be t squared. So what you're going to do here is write this as 1. Notice I'm going to follow this formula exactly. 1 plus, now u squared, u is t squared. So instead of writing u here, I'm going to write a t squared, and I'm going to square that because of that formula. Okay, so again, I'm going to write on here, u is equal to t squared. So that's what I'm getting that from. Alright, and then finally, du dx would be the derivative of t squared. Alright, so the derivative would be 2t. And I guess I should say the derivative of u with respect to t, and this one's du dt here. So this would be 2t. So I would write this as 2t. So the answer to this one would be 2t, 1 plus t to the fourth. And that's it. Alright, let's do one more here. We're going to follow this derivative rules, the table. Notice that I have the derivative of the inverse of the sine function. Alright, where tangent of theta, that is u. So u is the tangent of theta. Okay, so notice that I have that formula right here on top. So this would be equal to 1 over the square root of 1 minus tangent square theta, right? Because I square, notice that I'm squaring u. If I square this, I get tangent square theta times the derivative of tangent, which is u. So the derivative of tangent with respect to theta, in this case, that would be secant square. Okay? So this would be secant square theta And that's equal to secant square theta over the square root of 1 minus tangent square theta, right? So again, look at it again. I don't think, there's a lot of stuff in this note that's not really necessary. What's definitely necessary is this last part right here. Make sure to remember that. And definitely, you must know how to do this part right here. Okay, so example 3 and example 5 and 6 is really what you're looking at for the most part. All right, if you got any questions, please let me know. Watch this as soon as you can, but I guess if you watch this to the end, you have already watched this, so never mind, who am I talking to? Goodbye.